Alright, so write the equation for the solubility process. All of these compounds that I'm going to have here are insoluble salts, but insoluble ionic compounds. But everything dissolves to some degree. And so we have what's called the Ksp expression, and we only put in the concentrations of gases, or in this case aqueous. Solids are left off. So in a way it's going to be simpler, but you're going to see that there are ways of making this a little tougher too. So the calcium carbonate is a solid. It breaks up into calcium ion and carbonate ion. This is where it's important to know your polyatomic ions, so you know how this thing breaks up. Does it break up into 2 pieces, 3? Looks like it could break up into as many as 4 if you don't know what you're doing. So be careful, and go back to chapter 2, I think, and make sure you know your polyatomic ions. Most of them you will know, but aluminum hydroxide is a solid. It breaks up into aluminum. This one's fairly easy because there's the parentheses, but don't forget that coefficient out front. We just came off of chapter 16 where everything was 1 to 1, but now we don't have that anymore. We can have coefficients that can be any number. Usually it's going to be less than 3 or less, I should say, but it could be anything, so just be careful. Now here we have 3 magnesiums, and I put this one in here because this is about as tough as it normally gets. So the Ksp for this is going to be magnesium cubed. Now you should know the charges as well, but as long as you have the pieces right, even if you get the charges wrong, the math is going to work out. I hate to see magnesium with a +1 sign here, or this written with a -2 sign, but as long as you have this 3 and 2, you're going to get the right answer. So make sure you know the charges as well. So they wanted to know that's all they wanted there. Okay, so let's do a problem. And I'll make up some salts that just so that they're not the same as in your book. So we have this hafnium 2 carbonate. And what we do is we put a hafnium carbonate into water, mix it up. There'll be a lot of solid left on the bottom, so decant off the solution. We decanted off 2.5 liters of it. We assume that it's saturated with the hafnium carbonate. Then we dry it out, and we get 0.0043 grams of residue. Assuming that we done everything perfectly and everything was clean, then that residue is nothing but hafnium carbonate. So if we write it out, we have hafnium carbonate solid that when it went into solution, it went in as hafnium +2, and we may have to go to another. And I put just in here, I forgot to subscript the SP. So when you see that, it should be K subscript SP for solubility product. Now, the solid, when it breaks up into equal amounts of each of these, and we could call these X, positive X for each of these. And those concentrations would then go into our Ksp expression, which is going to be the concentration of hafnium times the concentration of carbonate. And so that's going to be X squared. Okay, so we have to determine what X is, and X is going to be moles per liter. So we're going to take grams, divide by the formula weight, or the molar mass of the hafnium carbonate. That'll give us moles. Divide by liters, that gives us concentration. So let's do that out. 0.0043 grams of hafnium carbonate. And the molar mass of this is 238. I did this earlier. So I double checked, but if I'm off on any of these numbers, the setup is correct. Let me know if I am wrong, but if this turned out to be 228 or something like that, that's okay. Send me that. Let me know if I made a mistake, and I'll make the correction, or we can work through the email to make sure that we get the actual answer. But just trust the setup is correct. And I just say that because some of these get pretty wild. We don't usually have to deal with molar masses and converting back and forth between them. We usually end stuck with just moles and moles per liter. So it can get a little dicey working with these. So not trying to make an excuse that it's okay that I made the mistake, but when I'm doing out so many of them, it's possible. So don't just give up on the problem because there's a difference in the answers to let me know. We'll work it out. So there's 7.24 times 10 to the minus 6 molar of hafnium carbonate that was present in the solution. We figured out the moles of it divided by the original volume of the solution. Well, see, hafnium, even though we don't put minus X here, there is a ratio, a 1 to 1 to 1. So for every mole of hafnium carbonate that broke up, we created 1 mole of each of these. So that means that the concentration of the hafnium ion, each of them is equal to X, is also equal to the concentration of the carbonate ion, which is equal to 7.24 times 10 to the minus 6 molar. Now, if these had broken up into 1 and 2, then there would be a 2 here, which means that the carbonate would be twice this. So now we got to be careful, because all the acid stuff we did earlier was 1 to 1. This one is 2 because I wanted to start out with something easy. But now we know what X is, we plug it in, and our Ksp is then 7.24 times 10 to the minus 6 squared, which is 5.22 times 10 to the minus 11. All right, let's try another one here. This is about as tough as it's going to get. We get this osmium, Osmium 2 Phosphate. Its molar mass is 760 grams per mole. Just to write that up there. Now, we do the same thing. We have a saturated solution. We dry out. We evaporate off all the liquid, and we're left with 0.000770 grams of the osmium. We divide by 760, and that gives us moles. And then 1.01 times 10 to the minus 6 moles divided by the volume, 3.75 liters, equals 2.70 times 10 to the minus 7 molar. And this would be Osmium 2 Phosphate. Now what does osmium do in solution? We want to write out the Ksp expression. Now this is a solid, but when it goes in, it becomes 3 osmium 2 plus and 2 phosphate ions per formula unit. So this is minus X, but we don't draw it because it's a solid. It loses that amount. This becomes plus 3X and plus 2X. So our Ksp expression is OS 2 plus cubed phosphate squared, or 3X cubed. Make sure you put the 3 in both times. 3 for the concentration and 3 for the exponent. 2x squared, and this comes up to be, where did I put that? This is 108 x to the 5th. So we have to determine what x is. So now we know that this is the concentration of the osmium, but the concentration of the osmium ion should be 3 times that, because we started out with that concentration of the formula unit, but then it broke up into 3 osmiums, and the concentration of the phosphate should be 2 times that. And this comes up to be 8.1 times 10 to the minus 7 molar, and this comes up to be 5.4 times 10 to the minus 7 molar. Now we have the concentrations of the osmium and the phosphate, and they go right in here. So we could do one of 2 things: either put these values in here, or since we already solved in terms of x, we could just take this as x and could plug it right in here. We'll get the same answer. But we'll do it this way, since I did these concentrations out. It'll be 8.1 times 10 to the minus 7 cubed, and then 5.4 times 10 to the minus 7 squared. I put this up higher as if I was going to put something below, a reactant below, but in all of these cases, everything we're doing in this chapter, there won't be anything below because the reactant is a solid. So I got to get used to that again. And this comes up to be 1.55 times 10 to the minus 31. It's a very small number. We should get used to those very small numbers for Ksp. We have some, look in the table, you see some that are larger, like 10 to the minus 5, but we'll see ones that are really, really low, like 10 to the minus 40, 10 to the minus 50. So we should get used to that.